All right, hello everybody. If you don't mind me, we're going to do another lecture on linear regression today. I just want to pop out my clock there so I don't run over time too much. And actually, I think with this one, this is the last lecture I'm going to give you on linear regression, at least per se. But I'm going to try to split it up into two parts. So we'll do the first half of this in part one and the second half in part two, as is only appropriate. But overall, it's part three of linear regression. And I'll start it off by saying I don't really have anything fun to offer you today. If you want to go back and play the Guess the Correlation game, you can always do that in your spare time. But I want to start off by talking about independence of variance and how that applies to our understanding of the correlation coefficient R. So let's get down to business. We've already talked about how R can quantify the correlation between two variables, X and Y. And we've also said that R can quantify how much variance in Y that there is that we can account for. I haven't really derived that explicitly, but I'm going to walk into that in a slightly different way at the beginning of this lecture based on something we've seen before in our mathematical wanderings. I'm going to try to make this lecture not as math heavy as the previous ones have been, but there will still be a bit of math for us to walk through. The majority of it, though, I'm going to just push back to the end of the lecture and some additional notes that you can look through yourself if you're curious. Something we have talked about before as we have walked through the math is that the variance in Y can be split into the sum of the variance of our predictions based on X and the variance of the errors that we make based on our predictions from X. So we're never going to be perfect, but the interesting thing is that this sort of split will be perfect. There's going to be a clear delineation between the amount of Y we can predict and the amount of Y that we cannot predict. And that will give us yet another way to characterize R. Okay, so where does this come from? So just so you know, this is part of the math that I'm sticking at the end of the lecture. If we have a variable that's the sum of two other variables, so let's call this sum variable W and the other two independent variables U and V, then the variance of W is going to be equal to the variance of U plus the variance of V plus 2 times the correlation between U and V times the standard deviation of U times the standard deviation of V. And I used to walk you through the derivation of how we get to this spot from just assuming that there's a sum here. It's actually not that complicated, but we don't need to dwell on it for too long. So I'll just say check out those slides at the end of the lecture if you're curious about that. But you might notice if you're comfortable and familiar with algebra that it kind of looks like we're just sort of squaring the term over here. If instead of U plus V, we just have like the standard deviation of U and the standard deviation added to the standard deviation of V. If you just square that term to get the variance, you're going to get something that looks like this, except that we're also including this R term here. So this is the correlation between these two variables, U and V. And the interesting case is that if that equals 0, if that correlation is 0, then the variance of W just equals the variance of U plus the variance of V. So we cut out all this sort of covariance stuff over here and the standard deviations of the two variables themselves, and we just are left with a pretty simple equation. The variance of W equals the variance of U plus the variance of V. Okay, that's in sort of this idealized case where the correlation between those two variables is 0, but that should hopefully make sense. Like if there is no meaningful correlation between two variables, then you can just add their variances together to get the total variance of their sum. Turns out we've kind of already seen this before because there's no covariance between the predicted and error parts of Y, or there's no correlation between those two parts of the dependent variable in our little linear regression analysis. We can apply the same sorts of standards to Y. So the variance of Y is just going to be the sum of the independent variances of those two terms. So the variance of Y equals the variance of the predicted values of Y, Y hat, plus the variance of the error terms of Y. And there's no correlation between these two parts. Okay, so having gotten to this point, by a little bit of hand waving, but not much, we can simplify this a little bit and learn how to express R in with a set of new expressions, basically. So we're going to divide both sides of this equation by the variance of Y. So on this side, we wind up with the variance of Y divided by the variance of Y. It's going to wind up being 1. That's why we're doing it. And then this side will be the sum of the variance of the predicted values of Y plus the variance of the error values of Y divided by the variance of Y total. And that will lead us to something that looks like this. We can split this part over here on the right-hand side, this fraction on the right-hand side, into two fractions because they're both divided by the same thing. And now I get 1 equals the variance of predicted values of y divided by variance of y, plus the variance in the error terms of y divided by the variance of y overall. This might look familiar. Actually, if it does, I'd be a little bit surprised because then you're paying maybe too much attention to all the mathematical details, but you might recall, if you go back into your notes, that the variance of the error terms of y divided by the variance of y is equal to 1 minus r squared. That was a step along the way towards figuring out what the coefficient of alienation was, which is basically the square root of this whole business over here. But on the next slide, we'll start with this stuff, but then we're going to make this substitution over here so that we can solve the whole thing for r. Okay, so this is where we were before. We're going to substitute 1 minus r squared for 1 minus r squared for this term over here on the right. And then, like I said, we'll solve for r. So the first thing we can do is subtract this business from both sides of this equation. We get 1 minus, in parentheses, 1 minus r squared equals the variance of the predicted values of y divided by the variance of y. On this side, if you can just do some quick house cleaning, the ones are going to cancel each other out. The negative signs are going to cancel each other out as well. So we'll get r squared equals the variance of the predicted values of y divided by the variance of y overall. And since this is a simple fraction, you can just look at it and say, well, the variance of the predicted values of y are going to be some percentage or proportion of the overall variance of y, because all we need to get to this is just add the error terms to it, the variance of the error terms to it. So basically r squared is going to be some number ranging from 0 to 1, and it's going to be the percentage of variance in y that you can account for by x in this idealized linear regression analysis. So that's nifty. That just basically gives us a number that tells us how predictable are these values of y based on what we know about x. And like I said, it's going to range from 0 to 1. That should hopefully make sense already anyways. You can kind of could have inferred that may be the case anyways, because we knew that r by itself, when it's not squared, would range from -1 on the low end to 1 on the positive end. So if you square that, you're obviously going to get something that ranges from 0 to 1. And we've been talking a fair amount about that special case where r equals 0, but that's going to be the limiting case for r squared, which, as you might recall, is known as the coefficient of determination, not the coefficient of alienation. All right, so why am I talking about this? So in our last how-to video, I walked us through an overview of what the results of an R linear regression analysis tell us. And most notably, what we focused on there were the t and the p-values for the slope part of the equation that a linear regression analysis will give us. Those t and p values for the slope will basically tell you whether that slope is significantly different from 0. So when r equals 0, the slope is going to be 0, and there's going to be no correlation between our two variables. And this analysis basically tells us whether we can do better than that, or whether we're doing significantly better than 0. So if the p-value, or if the t-value is sort of different enough from 0, the p-value will be less than 0.05. And if it is, you have significance. You can infer that there's a legitimate predictive connection between the independent and dependent variables, that you can use x to predict y to at least some extent in a meaningful way. But if that's not the case, if you get a p-value of greater than 0.05 in that analysis, then you can just describe the relationship between the two variables as 0, like there's no connection. They're passing each other in the night. So to make sense of this, and how this sort of analytical approach works, or this hypothesis testing approach works, we can still keep on thinking about what the world would look like when the null hypothesis that r equals 0 is true. So we're testing in this approach whether the slope is significantly different from 0. So the null hypothesis is that r equals 0. Okay, so in that case, we have no correlation at all. And I'm going to preface this little walkthrough by saying that, as usual, some helpful mathematicians have done the hard work for us. For pretty much everything else we're going to cover in this class, there's going to be a lot of math in the background that we're never really going to talk about explicitly, because smarter people than us have figured it out, and we can just use the results or the fruits of their labors, I guess you could say. But in this particular case, they worked out the fact that if you take two samples or take samples from two different populations for which the underlying correlation is 0, then you're going to get a variable t, which will be distributed in a t distribution shape, which will be equal to r divided by the square root of 1 minus r squared, there it is again, divided by n, the number of items in the samples, minus 2. And I was looking at this right before I decided to record this lecture, and I was like, wait, if there's no correlation, then wouldn't this always be equal to 0 because r is equal to 0? And I was like, no, wait a minute. It's different from that because there's no correlation between the two populations, but we're not taking every single item from both of the populations. We're just taking samples from them. So when we do that, we get a limited view of what both populations look like. And in that case, r will not necessarily be 0. It could be a little bit on either side of 0 is what we'd expect. And then, in fact, exactly what we'd expect is that that value of this variable, t, will be distributed like a t distribution around 0. So sometimes it'll be, or, the median number of times is that it will be 0 exactly, but a fair number of times it's going to be a little bit more than 0 or a little bit less than 0. But the further away you get from 0, the less likely you're going to get that value of t. I've got this little note here. We've got square root of 1 minus r squared again. There's the coefficient of alienation. It's not just a good band name. It's a useful mathematical concept. It keeps popping up everywhere you look. But anyways, the main thing to keep in mind here is that we're dealing with a t distribution, so we can run t-tests on what we get out of this little calculation. Okay, so that's nice and useful, and that's actually what the linear regression analysis does in R. And again, thankfully, we don't have to think about the technical details. We can just sort of read the output of the analysis or the module that we use when we run the analysis in R. So I'm going to show you a little bit of what I mean by this. And I kind of did this, I think, a little bit in the how-to videos. But let's say we're taking just random samples, call them X and Y, and we're just sampling randomly the numbers 1 to 100. We're just going to randomly pick them out of a hat. In this case, we're not replacing. Actually, maybe I should replace. Does this mean, yeah, I should. I'm going to change my notes when I post these. But in this case, basically what we're getting is just 100 random values of Y and 100 random values of X. Yeah, so I did replace, so sometimes we could get the same number more than once. Yeah, but basically what we shouldn't get is any meaningful connection between what's going on with Y and what's going on with X. So let's double check here and say, what is the correlation between X and Y? Oh, look at that, it's 0, or pretty much almost exactly 0. We can try this again, and maybe we'll get a slightly different value of R. Oh, look at that. For some reason, that's 0.2 in terms of its R value. So, whoops, not R, but Y. So, like, why is that happening? That's actually a slightly healthy value of R, even though I said there's not supposed to be any connection between these two. Well, guess what? You can get what looks like a connection between variables just through random chance. Most of the time, you'd expect an R value that's pretty close to 0. In this case, randomness has just worked in our favor. It looks like something is going on between these two. So we get an R value of 0.214. But is that a big enough R value to say that, well, underlyingly, this is not a connected set of variables? Underlyingly, can we still say that the correlation between these two populations is 0? So yeah, that's the question down here. And using our hypothesis testing principles, we're going to answer that question kind of in the way that you would basically expect, right? Yeah, so I'm going to come back to that in a second. Before I kind of walk you through the rest of that answer, which I have answered before sort of in the how-to video, I also wanted to take some time to look at what happens when we run a linear regression on a known linear relationship, so we can see kind of how that differs from the R equals 0 case. And so this is a case where we'd expect a perfect correlation between two variables, and we'll call those two variables not X and Y. but we will call them Celsius and Fahrenheit, or for short, we will call them C and F. So this is going to go back to the linear relationship that I keep harping on over and over again. So what I've done here is for the Celsius data set is just randomly sampled from -40 to 40 because I feel like these are pretty healthy limits for how cold you'd like it to be. In a place like Calgary is -40 at the limit, the lower end, and then the positive end is probably 40. We actually haven't gotten that close to -40 since I've been here. I think the coldest it's been is maybe something like -34 Celsius or something like that, -33. Not too bad, but when you get there, you feel it. And we actually gotten pretty close to 40. I think we got to 39. Anyways, just to give you some reference's sake, this is what these temperatures look like, and maybe these look like temperatures you might get in your corner of the world, wherever it might be, or whatever you're used to feeling. If I convert those into Fahrenheit, this looks something familiar to me from the good old USA. So 100 is a really hot temperature, -32 is a really cold temperature. Who cares what sort of numbers you're using to express it in, though, because if I just look at this correlation between these two guys, I get a perfect correlation. So I get 1. I get a linear relationship, and I can see that quite nicely if I just plot these variables out. And I see, well, down here on the bottom we have Celsius, and on the y-axis we have Fahrenheit, and it's linear, right? It's a perfectly straight line. There's just some gaps in here because I'm kind of selecting some of these C values at random before I convert them into Fahrenheit. Okay, so that's sort of the opposite of what, I guess we could still plot, and go back and plot our X and Y. We haven't gotten rid of those. Sorry, like this. Yeah, here's my, maybe there's something going on correlation. It doesn't look like there's something going on, but the math says there might be. I just don't know exactly how to interpret that. Yeah, so like I said, normally people are really good at seeing patterns. But if you're not seeing a pattern here, there's reason to maybe doubt that there is. In the Celsius and Fahrenheit case, it's obvious there's a pattern going on there, right? And we can confirm it. We can draw a linear regression line or a best fit line, and it'll go straight through those dots so they look like little beads on a string. Yeah, so goodbye star cluster or center of the galaxy. We've got perfect predictiveness. And in fact, if we run this linear regression analysis, the summary command on this linear model, it gives us this funny warning, which says, well, this is basically a perfect fit. So maybe something's gone wrong here. And what has gone wrong is that I'm, just being kind of dumb about this, and there's like obviously a linear relationship, so I don't need to like run this analysis, because the analysis is for cases where things aren't perfectly correlated with one another, and I'm trying to determine if they are, or if there is any sort of connection between the two. So again, what we see here is that in this particular case, actually just looking at this, it gives us the right estimates for the slope and intercept parameters of the linear equation, right? So my slope is going to be 9/5 or 1.8, and you can see it over here. Hopefully you can see the font that's that small, but the slope should be 1.8, and it's figured that out exactly. And the likelihood or the probability of that being different from 0 is very, very small. Or sorry, the probability of that slope coming from an underlying slope of 0 is extremely small. So we're going to reject that null hypothesis and say this is a significantly different value from 0. Same thing for the intercept. This is the scientific notation for expressing this value, but it's 32, right? So it's 3.2 times 10 to the 1 power, basically. So that's 32 right there. It's figured this out exactly right. Hopefully that gives you some confidence that there's value in doing this. And R is actually programmed correctly. And just it reports the R value here is 1, which we already know. So there's a perfect correlation. And if we actually try to run this, R is going to tell us, stop doing that. You're wasting my time. So, right, that's reassuring. And actually, as long as we have a decent correlation between X and Y here, let's see what the summary tells us about that. Okay, this is interesting. Because we had an R value of 0.21 something. If you square that, you get an R squared value of 0.0458. If you run this linear analysis, regression analysis for it, you actually get a slope, which we saw before is 0.214. And R, or the analysis, is thinking that might be different from 0. And in fact, this p-value is small enough that it's saying this is significant. So this is a case where you'd get a nice example of a false alarm. So we know that there's no connection between x and y here, but it's guessing that there is. And it's not, the smallest p-value we've ever gotten, but it's small enough, it's less than 0.05 to say that, oh, something's going on here. Maybe there's a connection between x and y. So, it's not just humans that do it. It's, mathematical analysis that can do it as well. And I guess mathematical analysis is just an extension of the way humans think, but the computer doesn't know that. Anyways, this is going to be different from 0, but that's less interesting because that's kind of the way we set it up. So this is what a false alarm looks like. Let's look at another sort of situation where we're doing this, taking this underlyingly linear relationship between Celsius and Fahrenheit, and I'm going to generate just a new set of random values for Celsius. And what I'm going to add to it is some noise for the Fahrenheit measures. And I guess I shouldn't have, maybe I'll just to assuage any concerns you might have. Oh, dang it. How did I do it to begin with? That's how I did it. Yeah, so what I want to do is just what I did before and just confirm to you that here's our C values. And if we do the summary command, we find that, we know exactly what the parameters are. And this is significantly different from 0. But what I want to do is add in, here, the correlation is 1. So, okay, I shouldn't have done anything there. But what I want to do is add some noise. So what I'm going to do is, instead of just converting Celsius into Fahrenheit by multiplying the Celsius values by a slope and then adding an intercept to it, I'm also going to add this error term. And we talked about this a bit before. Maybe I should load up the notes on that just so you can see them. And hopefully I can find them without too much difficulty. So, right. What I'm doing here is this equation. So I'm giving you the mx plus b, and then I'm also adding this error term, which we called noise. And the way I'm just adding that noise is that I'm randomly sampling, again, for a number between negative 40 and 40. And I'm going to have to do it 100 times because there's 100 values of C. And so if I do that, and maybe I'll move this up a bit so you can see a bit better, but it's going to look like that. And now I can check what is our new correlation between, first of all, look at like F and compare it to C. So let's get an easy value here. So a value of 1 degree Celsius should be 1.8. Value of 1 degree Celsius should be a value of 33.8 Fahrenheit. And I think this one gives us like negative 10.2 if I've got that lined up right, or it's something like that. Let's start with this one. So negative 12 is, it's 10.4 Fahrenheit, and I wind up with a value of negative 3.6. So I'm adding some noise to it. And now let's look at the correlation. And before we had a correlation of 1. Now it's not perfect anymore because there's some noise in the situation that I'm adding to it. And we can also look at the plot. Sorry, I keep getting distracted by these various ideas, but I think they're all helpful to some extent. And I think this plot will definitely be helpful. So before we had that perfectly straight line, right? And now we have what looks like a linear relationship, but there's scatter on either side of kind of the central linear value in the middle. So, I mean, the other part of this is I kind of had to limit the error. The error is not, I guess, what you would say normally distributed around this line. It's sort of linearly distributed because I'm grabbing on either side from negative 40 to 40. So there's limits on either side, and I'm not like preferentially getting closer to the line than I am further away. It's just adding some number to it. But you can see there's like a line here with scatter. And if you can't see that clearly, I can just put the line in the middle by drawing the best fit line right through the middle there. And you can see there's these scatter of points on either side. And you might also notice that this doesn't look like the exact same line we saw before. It actually is going to have a different slope and intercept. And we can check to see what those are right here. So before, our regression analysis had predicted the relationship perfectly, right? Because it was a perfect fit. So before we had this slope of 1.8, and now it's 1.93. The intercept is supposed to be 32. This one's 31.947, so on and so forth. So those aren't perfect anymore because now we have noise in the equation. Normally what you'd expect to see, though, is that the estimate plus or minus the standard error should have the true intercept or mean or slope in them. We see that with the slope intercept, so 31.94 plus 2.16, whatever. That's going to be a bigger, higher end of this estimate than 32. So we're good there, but we're missing it in terms of the slope. So if you remember, we're doing our confidence interval calculations. Here we have a slope estimate of 1.939. You can subtract 0.09 from that, and you wind up with like 1.84 something. So that's going to miss the actual slope value here. And you can kind of see that it looks like a little bit of a shallower slope here, just because we've added noise to this. So we're not, going to get a perfect analysis anymore because we don't have a perfect fit. But normally, if, we're normally in stats, we're dealing with situations where we don't have a perfect fit. If we do have a perfect fit, we don't have to worry about this stuff at all, or using these methods at all. We can just say, oh, look, there's a perfect connection here. We can use math, not stats. And yeah, so there we go. That's just reiterates what I said already. Going back to this standard error stuff, though, just so you know, there's an equation for calculating the standard error of the regression slope. It looks like this. I walk you through how to use that in the how-to video that I've already made after the second linear regression video. I'm not going to walk you through the derivation of this. You don't have to worry about that anymore because, number one, it's not super important that you know where it comes from, but number two, I actually don't know what the derivation is, and look at me, I'm still alive and still teaching stats somehow. Anyways, yeah, as an aside, if you're still watching this, it reminds me of when Canada legalized marijuana, and not that I smoke or endorse smoking marijuana at all, but I remember for many, many years, for most of my life, people were like, oh, if you legalize marijuana, the whole society will just collapse. And look, Canada is still pretty nice, and it's been like 3 years. Marijuana does not destroy society, and not knowing all the mathematical details will not destroy your mind as long as you understand the general concept of where these things are coming from. The other part of this that I want to get across is that if you divide the slope estimate for the regression line by the standard error, you're going to get the same t-value as what you'd get from that equation that I started this lecture off with. So this t equals r divided square root of 1 minus r squared over n minus 2. That will give you this t-value here. And I'm actually going to, this is what it looks like for Fahrenheit and Celsius. It's going to be easier to see, I think, if we go up to our x and y calculations. Yeah. So for this random connection between x and y, here's our slope estimate, which is 2.214. If we divide that slope estimate by the standard error for that estimate, 0.099, we get a value of 2.169. And that's basically, the math tells us that should be distributed in a t-shaped distribution, so we can run this sort of t-test analysis on it. And this is sort of far enough away from zero that the p-value winds up being less than 0.05. But that's where that comes from in sort of this approach, but we get the same t-value if we do it this way here. And I'm not going to do this twice, but I showed you exactly where that comes from in the previous how-to video on this sort of regression analysis. So I'll just leave it at that for now, and then walk you through one more thing with the output of this regression analysis, and that's how to figure out what the significance of r squared is. Going back, this will tell you whether this slope value is significantly different from zero. It thinks it is, even though it shouldn't. And this will tell you if the intercept value is significantly different from zero. It definitely thinks it is, and it should, but we don't really care because it's just the intercept value. Down here, we get a value of r squared, which is 0.0458, which is basically this squared. And then it tells us at the bottom this thing called an F statistic. And it gives us the value of the F statistic it gives you 2 different degrees of freedom for it, and then it gives you a p-value. But what this F statistic is interpreting basically is whether this R squared value is significantly different from 0. And maybe, this kind of gives us reason to just sit and wonder about this a little bit. But this R squared value is pretty small. We said it can range from 0 to 1. It's only 0.0458. But based on this analysis, it's saying, oh, it's significantly different from 0 because our p-value is less than 0.05. And you might be thinking, maybe it's significantly different from 0. That's not a big effect size. But where does that F statistic come from? It's basically that old variance test that Ronald Fisher came up with, and we talked about when we were still learning how to do t-tests. We wanted to figure out are variances equal or not. This F test is basically telling us whether variances are equal or not. And the variances that it's testing are the variance of the predicted values of y and the variance of the residual or error values of y. And in fact, I use the term residual here without introducing it, so I'm going to call it error right there. But to see what this looks like, here's how we calculate that F statistic. It's the variance of the predicted values of y divided by the variance and error values of y. And then I multiply it by n minus 2, or the degrees of freedom in this particular situation. And I'm getting n minus 2 here because I have 2 samples. Remember, I'm looking at the connection between x and y. So like the variance of the predicted values of y, that's just the percentage of y I can predict. And then the variance in the error values of y is just the percentage of y variance I can't predict. So you could draw this up in a variety of different ways, but you're basically looking at that ratio. So one part of this is that the bigger this ratio is, the more of y you can predict. And so the bigger F is, the further away it will be from 1. And the more likely you are to be able to make some meaningful predictions about the values of y. This value doesn't come out of nowhere, interestingly enough. F is actually equal to the square of the t value for the slope, or in other words, F equals the t squared, where t is that equation I showed you on the previous slide. In the first 5 example, which I walk you through in the previous video as well, we get a t value of 3.428, and if you square that, you get an F value of 11.75. And we see the same thing here, basically. This value squared should wind up being 4.70. This value squared, 2.169, should be 4.704. And we can kind of confirm that by just doing this. Oops, maybe. Yeah, 4.704 with some rounding off errors there a little bit. That's where that F value comes from. We can do the same thing for this guy here. So 21.12. Can you tell me what that's going to be if I square it? Yeah, it's going to be this, 446. And of course, I get the same p-value for those because I'm basically testing the same thing in 2 different ways. So just to show you the math where that comes from, if I start off with t looking like this, r over this square rooted mess, if I square that, then I get r squared over this fraction, 1 minus r squared divided by n minus 2. I can kind of flip that fraction in the bottom to convert it to this, where I have r squared divided by 1 minus r squared times n minus 2. All of a sudden, this should kind of start looking familiar, right? This is kind of that ratio we were concerned about. So r squared is just the percentage of y that I can predict, and 1 minus r squared is the percentage of y I can't predict. So if I just kind of like take the ratio of those percentages, I get t squared equals the percentage of y I can predict or the variance in the predicted values of y divided by the variance in the error values of y times n minus 2. That is equal to F, like that. So basically, the more variance you can account for in y, the higher the value of t, or F, will be, and the more likely the hypothesis test you run as part of this linear regression analysis will yield a significant result. So this connection between t-tests and f-tests basically leads us directly into the technique of what's called analysis of variance, or more commonly it's called ANOVA. and that will form the basis of our next unit in this class, and that will take some time for us to walk through, but this is a very commonly used statistical technique, especially when you're dealing with sort of multiple independent variables potentially predicting one dependent variable. And as long as we're here, I'm going to give a little nugget to those of you who have watched to this extent, this video to this point. But how do you report these F-statistic values? So I said you can use, this is basically an attempt to interpret whether this R-squared value is significant or not, this little F-statistic reporting down here. So maybe you recall this from when we ran our variance test, maybe you don't, but you can report it by saying got F of 1 and 98. So there's two different degrees of freedom there, 1 and 98. And then that is equal to the F statistic itself, 4.704. And then the p-value is this, 3.03251. So this is how you'd report that result here. And of course, since it's less than 0.05, since this p-value is less than 0.05, you say that's a significant result. So this R-squared is significantly different from 0. But I was kind of alluding to this before. This is a very small R-squared value. Even though it's significant in the statistical test results, it really shouldn't be. You just don't know that if you don't know where those results actually came from. So that's the conclusion you draw in this case. And then you could also acknowledge that this is a pretty small effect size, but it's there. Something's going on just through random chance in this particular case. So I'm not going to say anything further about that, but I will say the F statistic tests that value of R-squared, whether it's significant or not, and this is how you report it. So that may be of some use to you if you do the homeworks later on. All right, that's all I'm going to say for now. I'll talk about part 2 of this lecture here in just a bit. See you then.